Okay, so good evening, Monty, and good morning, everybody in Taiwan. Yeah, today is really my great pleasure to invite Dr. Montie Avery from Post-State University to give us a talk about his recent research. The title is about universality. Wow, this is a fancy word, and it's spreading into unstable states. So this is basically about so-called marginal stability conjecture. And then they can study many dynamical properties of traveling wave without using the comparison principle. This is the main keyword, okay, main sentence. And we are very curious about this. So let's welcome Dr. Montie Avery. Yeah.
Great. Thank you. Thank you for the introduction, and thank you very much for inviting me to speak in this seminar. It's a great opportunity to talk to some new people, and yeah, kind of fun to give a seminar in the evening. It's kind of funny also, I guess the date is right or wrong depending on whether you're in the US or in Taiwan.
Yeah, I once
But
upon gave a seminar talk in the midnight, 2 a.m. in the Chinese New Year
oh
day.
wow.
So,
Wow. Yeah, this is not so bad. This is pretty comfortable. Okay, so then let's go ahead and get started. So yeah, so in my talk I said something, or in my title I said something about spreading into unstable states. So let's first sort of talk about what that means and why you'd be interested in that. So basic definition is that a state is unstable when small perturbations of that state lead to large changes. Um, Now, a first objection someone might have is, well, why should you ever see unstable states, right? Then if they're not robust against small perturbations. And there's a couple different contexts in which these might come up. One is if your system undergoes some kind of bifurcation, then a state that used to be stable suddenly becomes unstable, right? And so you'll be near that state, which is now unstable, and you have to see what happens next. And another setting when this can happen, yeah, in these like ecological or like infectious disease models, for example, um, the system could have always been unstable against the introduction of some invasive species or some new disease that just really wasn't there before. So in this way, you can see these unstable states even at sort of large amplitudes, not just near bifurcation, if it's really an instability against something new that just wasn't there before. Okay, and so when you have one of these instabilities, you're going to go away from that unstable state. So you're going to transition from that state to another one. And often, and this is what I'm going to focus on, often these transitions can be mediated by traveling fronts. So you have some old state here, which now becomes unstable, and then you have a new state which spreads and invades this unstable state with some characteristic speed. And so the fundamental questions you might ask are, how can you predict this speed of propagation? And then what state do you expect to see in the wake of instability? What's the new state that's selected? Okay, so here's an example where you can see this. So this is the Swift-Hohenberg equation. So it's this fourth order in space PDE that models pattern formation near what's called a Turing instability. And so in this equation, if this parameter mu is positive, then u equals 0 is an unstable equilibrium. And if I simulate this equation with an initial condition that's just uniform white noise everywhere, so everywhere in my domain there's a little bit of small noise, then this is what happens. This noise sort of evolves into this pattern. There's still some sort of coherence here in that there's a sort of selected wavelength, right? Pretty more or less everywhere here. Like the wavelength here is pretty much the same as the wavelength there. But on the other hand, this pattern is still in a lot of ways fairly disordered, right? We have stripes of all these different orientations, and they have to come together where their orientation changes, and you have these sort of defects like you see here. And so while there's still some kind of selected wavelength here, there's still a lot of defects and disorder in this pattern. Okay, so then let's look at a different kind of experiment where in the previous one, we had noise everywhere in our domain, so we grew our pattern everywhere at once. So here what we're doing is we just have a little perturbation in the middle of the domain, and our initial condition is identically 0 outside of this little strip in the middle of the domain. And let's see what happens then. So then we see the solution grow and invade this unstable background state. But now it seems like there's maybe a little more order to this pattern. There's still some defects, but somehow there's kind of a preferred orientation here. Like we're only seeing these stripes that are kind of going pretty much in this vertical direction, and we're not seeing stripes, for example, that are going in this horizontal direction. So somehow the fact that we're growing these patterns from this localized initial condition is sort of determining some kind of features of the pattern that we see. And this is the kind of thing that we'd like to understand, both how fast does this spreading happen, and also what do we see behind the spreading. Okay, and there's really a lot of examples of different models and physical systems where you can observe this kind of phenomena of spreading into unstable states. For the sort of very classical one, which I'm sure you're mostly familiar with, is the Fisher-KPP equation, which originally was used to model genetic drift all the way back in 1937. Here's a sort of actual picture of an experiment of crystallization fronts in organic semiconductors, where you see this pattern forming as time moves on this way. Here's some more experimental data, now from some sort of classical experiments in fluid mechanics. Here is Rayleigh-Benard convection, and here is a Rayleigh-Taylor instability experiment. So these are sort of measurements of either temperature or velocity profiles of the fluids, and you see these sort of fronts spread and develop these periodic patterns in their wake. And there's lots more different examples, and a good place to look for these is this review article of Van Sarlos. Okay, so let's start from sort of where it all began, at least on the mathematical side, which is the Fisher-KPP equation. And so if you ignore the diffusion term in this equation, then you have this logistic growth ODE. So you have 0 is unstable equilibrium and 1 is a stable equilibrium. And this diffusion sort of gives you some spatial interaction between these two equilibria. So if you simulate this equation with this small localized initial condition, then what happens is your solution grows until it saturates at the stable state 1, and it spreads outward with some characteristic speed. So in this example, you'd be interested in predicting what speed this is. Okay, and now I'm going to make one simplification. So in the first couple simulations I showed you, I was interested in spreading from compactly supported initial conditions, right? Just a small compactly supported perturbation. How does that spread? What speed gets selected? So to simplify things a little bit, I'm going to replace compactly supported with what I call steep. So steep basically means it's compactly supported on one end. Or it's at least very rapidly decaying on one end. So now if we look at the Fisher-KPP equation with that kind of initial condition, here it's a Heaviside step function, then we see our solution evolves into this traveling front profile, which is moving with some speed. So the advantage here is that now we only have to describe one of these front interfaces instead of two, but hopefully we're still capturing sort of the spreading dynamics from localized initial conditions. And yeah, it appears here that this is converging to some uniformly translating traveling wave profile, and we'd like to understand why that is. So if you're a dynamical systems person, then the first thing you might do is say, okay, maybe we can figure out what thing this is converging to by just looking for a stable traveling front solution. So if you make this ansatz into the PDE, you get this traveling wave ODE, and you can look for stable traveling wave solutions. The problem is, if you look at this ODE, these fronts exist for a lot of speeds. Actually, all positive speeds, you have one of these fronts. But there's some differences in what these fronts look like. So the fronts with speeds less than 2, they're non-positive. They have these oscillatory tails, the way that they come into 0. And then at c equals 2, there's some kind of transition where these two complex eigenvalues here come together into a Jordan block. And then after this, these fronts are positive and monotone. So this isn't telling us which front we see because there's fronts for all different speeds. There's a bunch of different fronts. Now you can say, okay, but I said we should look for stable traveling waves. The problem is if we restrict to small enough, localized enough perturbations, all of these fronts with speeds bigger than or equal to 2 are stable. And so that's still not telling us which one we expect to see when we have a steep initial condition. But for the Fisher KPP equation, this has been well understood for a long time. Going all the way back to KPP in 1937, they proved that if you solve this equation with heaviside initial data, then if you go to the frame that's moving with this speed 2, you converge to this traveling front solution. So the selected speed is 2, and the selected front is the front that moves with speed 2. And since then, there's been a lot more work on this. With probabilistic methods, Bramson got this next order term in the front position here, this -3/2 log t, which has since been reobtained using more sort of direct PDE methods, and then also including higher order terms in this position for the solution profile. And what's going on here is that the Fisher KPP equation has a comparison principle, and that's what this is all kind of using. Even back to this argument of KPP in 1937, this is some kind of zero number, intersection number type comparison principle argument. And so now the problem is a lot of equations don't have comparison principles. So how are we going to make these predictions for invasion speeds in other systems that don't have comparison principles? And the thing that we use to do that is something called the marginal stability conjecture, which in the physics literature goes back a long time, Dee and Langer in the 80s, and you can sort of look even farther back in the plasma physics literature, like the Landau-Lifshitz book series. You can find these ideas floating around in there. And what this conjecture says is that the fronts which are selected by steep initial conditions are those which are marginally stable. So if we look at what happened in the Fisher KPP equation, I said that all of these fronts with speeds bigger than or equal to 2 are stable. These ones below are unstable. So the front that was selected was the one that was just at the boundary of stability. And so this marginal stability conjecture is saying that this is what happens in general. So what that means, if you're just at the boundary of stability, then you're going to have some marginally stable spectrum, some spectrum that's touching the imaginary axis somewhere. And there's two ways it can do that. That critical spectrum can either be essential spectrum or it can be point spectrum. And then there's a couple more subcases you can divide that into. This touching the imaginary axis can either happen at the origin or it can happen at some non-zero frequency. So if this touching happens at the origin, then we expect to see a front profile that's uniformly translating, just moving along but maintaining a fixed profile. If this touching happens at some non-zero frequency, then we expect this front to kind of be oscillating as it propagates. So when the marginal spectrum is essential spectrum, we call these fronts pulled fronts. The basic reason, or one way you can think about that, is essential spectrum is invariant under compact perturbations. So the essential spectrum can be determined just by looking at the linearization about the unstable state in the leading edge. And so just by looking at the linearization far ahead of the front at the leading edge, you can predict this speed here if it's a pulled front. And so that's kind of the idea, is that these dynamics are really being governed by what's going on far ahead of the front, captured in this essential spectrum. And so we call those pulled fronts. Whereas when you have critical point spectrum, then you have a localized eigenvalue that's marginally stable, that's sort of giving you the critical dynamics. And this eigenvalue is kind of localized into the front interface. So the idea is that sort of what's moving you along is the dynamics in the front interface. So we call these pushed fronts. Now, when you have pushed fronts, you often have this picture where you have a spectral gap. You can stabilize the rest of the spectrum and you have just an eigenvalue here. And so then you can use kind of classical semi-group theory methods to analyze stability and selection from steep data of these pushed fronts. So I'm going to focus then on the pulled case, which is more difficult than the pushed case because you have to deal with this essential spectrum. But I'll focus on stationary invasion, not oscillatory invasion, just to kind of simplify things a little bit. Okay, so then our goal is to make this marginal stability conjecture precise and prove some version of it. So to do that, so this marginal stability conjecture is a broad statement. It's sort of saying that whatever your model is, you should be able to characterize the invasion speed by looking for the marginally stable fronts. So we want a reasonably large class of models to be able to sort of phrase this as a precise theorem in. So what we look at is, okay, so first with Arndt-Scheele, we looked at scalar equations, but with sort of an arbitrary elliptic operator here. So elliptic meaning of arbitrary order. It could be a fourth order elliptic operator, sixth order elliptic operator, etc. And then I extended this to where you have multi-component models with arbitrary number of equations here. And here I'm writing a multi-component reaction diffusion system, but you could also have some higher order diffusion in here, like fourth derivatives or something like that if you wanted. And then we want to study spreading into unstable states. So I'm going to assume that we have an equilibrium, u equals 0, which is unstable. Okay, so then the main result is that in this setting, this marginal stability criterion is the right criterion for predicting front speeds. So marginally stable fronts are selected by steep initial conditions. And the goal for the rest of the talk is to sort of formulate this result precisely and give some ideas of the proof and some applications. So sort of as a more detailed outline, first I'll talk about why marginal stability is the right thing. And then I'll sort of precisely formulate this theorem. What are the exact assumptions that you need to capture this marginal stability? And what's the exact theorem we can prove under those assumptions? Then I'll talk a little bit about some of the technical aspects here involved in sort of the theorem and its proof. I'll talk a little bit about, so the way this is structured is we prove a theorem that says, assume that you have an equation that satisfies these assumptions, then this is the predicted speed in this equation. So then I'll talk about how you can go about verifying those assumptions so that you really get a prediction for the speed in a particular equation that you're interested in. I'll talk a little bit about some applications using these sort of ideas to verify these assumptions. And then I'll talk about some progress towards genuine pattern forming fronts at the end. Okay, so first, why marginal stability? So we're focusing on pooled fronts, where I said that everything's kind of really governed by this unstable state in the leading edge, sort of, and this is pulling the front along. So let's just look at the linearization about that unstable state. And then what I'll also do is I'll look at that linearization in a moving frame. So as I'm watching the dynamics, I myself am moving relative to these dynamics, and that gives me this parameter C. Now, if I don't move at all, right, if C is equal to 0, then this background state, u equals 0, is unstable, right? And so perturbations to that background state will grow and spread. And so if I'm not moving at all, then at any fixed location, I'm eventually going to see this growth, see this instability, right? And that carries over if I move slowly. If I move slowly, this instability is eventually going to catch up with me. Now, on the other hand, what if I move very, very fast? Then it's possible that even though my solution is still growing in norm because of this background instability, I'm moving so fast that it doesn't catch up with me, that at any fixed location in my domain, I don't see this growth because I'm moving so much faster than this growth. And that's sort of what you call convective instability. So if we have these two pictures, one at C equals 0 and one for C very large, then there has to be some kind of transition in between where I'm basically just keeping up with this growth, just keeping up with this instability. And that speed at this boundary between absolute and convective instability is what we call the linear spreading speed. So it characterizes, it's the speed that where I'm moving, I see marginal pointwise stability. Okay, so why should that tell us the front speed? So let's look at sort of a picture or like a cartoon picture of what might happen. So we want to understand spreading from steep initial conditions. So one way to get a steeple initial condition is, let's assume we have a front solution to our model. So this is a traveling wave that looks like this. And then let's just cut off its tail. Just somewhere we, instead of taking the front, now we just set our initial condition identically 0 here and ask what happens then. So then out here, since my initial condition is identically 0, it's sort of reasonable to expect that my solution might be governed here by the linearization about u equals 0. But I want to look at this in the frame that makes this traveling wave stationary. So I'm going to this frame that's moving with the speed that comes from the front that I started with. And so since I'm looking at this in a moving frame, that's going to affect what my dynamics in the leading edge look like. So if my speed is too slow, then I'm going to have this exponential growth in the leading edge that we saw. Whereas this front is, if I didn't cut off its tail, it would be a totally stationary solution in this frame. So back here where I resemble the front, my solution probably shouldn't be changing that much in this frame, moving with the front's own speed. So I can't really reconcile these two things. Here, my front in the wake is more or less constant in time, but these dynamics in the leading edge are exponentially growing. I can't really reconcile these things. So that tells me that maybe this is the wrong speed. And the same thing is true if I look at a speed that's too fast. Now my front's still pretty much stationary back here, but my tail of my solution is exponentially decaying in time, which I still can't really reconcile with something that's more or less stationary. So the one speed where I have a chance of making this work is the speed where I don't have growth or decay in my leading edge, because then the front is constant back here and my tail dynamics are also constant in time up here. So then I can hope that maybe I can sort of match these two things together and get a solution that rebuilds its tail and propagates with this speed, this special speed. Okay, and this is basically the sort of big picture of the proof, is to understand these marginally stable dynamics in the leading edge and get a sort of good detailed construction of this tail of the front here, and then glue this to the front solution in the wake, and then show that you can actually do this gluing. So some kind of stability argument that controls the matching errors that you make here. That's sort of the big picture idea of the proof. Okay, so the first key ingredient then is understanding these marginally stable dynamics in the leading edge. So how do we capture those? So let's look at a simple example. So this is what would come from the Fisher KPP equation, basically, right? So we have a scalar reaction diffusion equation, and we're linearizing about an unstable state u equals 0 and looking at this in a moving frame. Now, this notion of growth or decay in the leading edge, I don't care about growth or decay in an overall spatial norm. What I care about is if I fix an x, is my solution growing or decaying in time, right? That's what allows me to match with this front back here. And so that property isn't changed by sort of multiplying by some function of space here, right? So here I'm using this sort of spatial exponential weight. And that maintains whether I have pointwise growth or decay, so I'm allowed to do that, right? It doesn't change the property that I'm looking for. So if I do that, then I get a new equation for V where this exponential weight parameter eta now shows up. And I have the freedom to choose eta however I want to choose it. Now, what I want is, okay, so I can rewrite this equation like this. So I have the second derivative here, and then I have these second and first derivatives here. And I want to choose eta and c so that I have what I want, right? Which is marginal pointwise stability. So I'm on my solution to neither be growing nor decaying at a fixed x, right? So this term would be a problem then, right? Because if this term is not 0, then my solution would be either exponentially growing or exponentially decaying in time, right? The solution to this is something exponential growth or decay. So I don't want that term to be there. This term is also a problem, right? This is this sort of mechanism that can produce, for example, exponential decay, right? If this term is too large, then I can get decay at a fixed location by this sort of sweeping out convective effect. So I also don't want this term to be there. So then, since I have the freedom to choose both eta and c, I can get rid of both of these two terms that I don't want. So I choose eta and c to solve this system of two equations. I get from setting these two terms equal to 0. And if I do that, then I'm left with something that maybe has a chance of not being growing and decaying in time, at least not exponentially in time. And you can see that this calculation is kind of equivalent to something else. So if I look at my original equation and I define what I call a dispersion relation, that I do just by sticking in e to the lambda t, e to the new x into this equation, then I get this algebraic equation. And these two conditions that I found up here, these are saying that I have a root of my dispersion relation if I choose c and eta appropriately. And this is a double root in nu. That's what this condition says, that the derivative of the dispersion relation with respect to nu is also 0. And so it turns out that this is a way to characterize this marginal pointwise stability. It's characterized by double roots of the dispersion relation. And there's this sort of additional weird pinching condition here. So they're called pinch double roots, but I'm going to sweep this under the rug. That basically you look for double roots of this dispersion relation, which is good because this is just algebra, right? This is something about roots of polynomials. So you can really try to compute this. Now these ideas go back to, early in the plasma physics literature, other places in the physics literature. There's sort of a very nice modern mathematical perspective by this paper of Holzer and Schill from 14, that's where I'd recommend looking if you want to read more about this. Okay, so that was in sort of a simple example where we just had a second order scalar equation. So now what would happen if we had a more general scalar equation, maybe with some higher order derivatives here? Then if we do the same thing, we start with our linearized equation, we get this dispersion relation, and we choose c and eta, the exponential weight parameter, so that we have a double root of this dispersion relation. Then we have a similar result here. We've gotten rid of the lower order terms in this equation for v, the weighted variable. And now we have at leading order a diffusive equation for v, and then maybe there's some higher derivatives here too. But what's going to be actually relevant for the dynamics here is sort of the large spatial scales, not like small frequency, not regularity. What's really important is the large spatial scales. So these higher derivatives are sort of less important. For these long-time dynamics, it's really the leading the lowest order derivatives that are really governing things. So we get basically the same picture in these higher order equations, that just by looking at double roots of the dispersion relation, we recover marginal pointwise stability, and we see these diffusive dynamics in the leading edge, which are going to play a role later. Okay, so the nice thing there was that in the scalar equation, this dispersion relation is basically exactly the symbol of the linearization, right? You just replace your derivatives with nus, your x derivatives with nus, and your time derivatives with lambdas, and you get the dispersion relation. And so by making assumptions on the dispersion relation in this scalar case, that you have these double roots, that immediately tells you stuff about the linearized dynamics here. You can just tell what the linearization is. Now, what if we have a multi-component system? Then if we sort of make this same ansatz, u equals e to the lambda t, e to the new x, then the condition we get is more complicated now because we have multiple components. The dispersion relation, we still have the symbol of our operator in here, but then we have to take a determinant. It's kind of like we're looking for an eigenvector somewhere, so we take a determinant. And so the challenge is that if you assume things about the dispersion relation, it's less obvious what that tells you about your linearized dynamics, because you sort of have to undo this determinant to get back to the linearized equation from the dispersion relation. But it's still true that pinch double roots characterize pointwise growth, and so you can use them to predict linear spreading speeds. And it's still true that sort of generically at the linear spreading speed, you have these diffusive dynamics in the leading edge, but you need to work harder than in the scalar case to figure that out. And so I just want to mention that that's the key thing that's different when you have multi-component systems. So after now, I'll focus on scalar equations just to kind of simplify things. Okay, so hopefully that gives you an idea of why marginal stability might be the right thing. And so now I want to formulate this main result more precisely. Okay, so the first key condition is this marginal stability in the leading edge, which is what we've just been talking about. So we assume that there's some linear spreading speed at which this state u equals 0 is marginally pointwise stable. That is, if we look at this linearized equation with compactly supported initial conditions, the solution at a fixed location, not in a norm, but just at a fixed location, is not growing or decaying exponentially in time. So that's this marginal pointwise stability, which can be characterized by double roots of the dispersion relation. The nice thing about that is that, like I said, this is an algebra. It's something about the roots of polynomials. So in principle, it's easy to compute these spreading speeds. At least you could compute the roots of these polynomials numerically. And that's this last reference, this paper by Arne Scheel, sort of talks about some efficient numerical algorithms for computing these double roots, these spreading speeds. Okay, so then in this picture I showed you before, I said the first key ingredient was understanding these tail dynamics in the leading edge. That's sort of will all come from this hypothesis one. Then the next thing is that we wanted to match these tail dynamics with a front solution in the wake. So we're going to assume that we have a front solution in the wake to match with. So we assume that our equation admits a traveling wave solution, which converges to our unstable state in the leading edge and converges to some new selected state in its wake. And we also assume that this convergence in the leading edge has these asymptotics. So it turns out that these double roots of the dispersion relation are associated to a Jordan block somewhere in the traveling wave formulation. So that's what you're seeing here is these sort of Jordan block type decay where you have this c times e to the minus eta c. So this is actually sort of the generic way for a front to converge to 0, given that the first assumption. Then you have this Jordan block hanging out here, and we're just saying that you have sort of the generic convergence in this Jordan block. Okay, so let's sort of.
I have a question. So
yes.
this Jordan block convergence rate is a consequence of a hypothesis one, or you need to assume?
So it will. So the fact that you have a Jordan block in the traveling wave equation is a consequence of hypothesis one. Now, what's possible is that this coefficient could just be 0. This A could be 0 for some reason. So, but that's highly non-generic. That's like a codimension 1 condition. So you need to assume that this happens. And I think I'll maybe have time to briefly mention this later. So if this coefficient A is 0, what that says is that you're not really in the purely pulled front regime. You're right at the transition point from push to pulled front propagation. So that's a paper Arndt, Matt Holzer, and I wrote. We sort of described this bifurcation sort of generically. And so this coefficient 0, then if you vary a parameter in your equation in one direction, you'll have pulled fronts, and if you vary in the other direction, you'll have pushed fronts. So we're kind of excluding that, saying we want to focus on actual pulled fronts here, not at this transition.
Yeah, but then in reality, how can you verify this condition? I mean, when A is non-zero.
Yeah, so I'll mention that a little more later. So one way is like perturbatively, maybe near some limit where you understand your equation, where your equation's simpler, you understand it better, maybe you can prove that this property persists as some parameter is varied. And then another way is numerically, and I'll mention that a little bit later.
Thank you.
Yeah. Okay, so let's step back and sort of see where we are now. So I said this picture is kind of the big idea of the proof, right? That we want to understand these tail dynamics of our front. So that's really coming from hypothesis 1. And then we want to glue this to a traveling wave solution in the wake. So that's really that traveling wave solution is coming from hypothesis 2. And with these two ingredients, we can formally do this gluing. We can do some kind of matched asymptotics that matches this tail to this front in the wake. But what we want to show is that that approximate solution that we get by doing that matched asymptotics, doing that gluing, is stable, so that there are actual solutions to our equation that do look like that. And so for that, we need more, because with just hypotheses 1 and 2, this thing could be unstable, right? It could be unstable in a couple different ways. There could be some kind of instability in the front interface. So that would lead to a pushed front. So that would sort of accelerate the propagation if you have some instability in the interface. And then what you should do is you should look for a pushed front that's moving with a faster speed. Now, there could also be an instability sort of far in the wake here, like the state that this front is selecting could itself be unstable. And that will lead to usually a staged invasion process where you might have at first this invasion happening in the leading edge, but then this thing is also unstable. So you have some secondary invasion happening here. So if we want to see just one invasion process with pooled fronts, then we want to exclude both of these things, instabilities in the front interface and in the wake. So hypothesis 3, we do exactly that. We assume that the state that we create, U minus, in the wake of our invasion process, we assume that it's stable. Now, I want to talk a little bit about, or I don't really want to, but I kind of have to talk a little bit about how this translates to sort of spectral properties of our linearization about the front, so to make this a little more precise. So if we take our equation, we have this front solution from hypothesis 2, we linearize about it, and we get a linear operator L. Now, since the essential spectrum of a linear operator is invariant under compact perturbations, it's determined by the linearization at plus infinity, called at the leading edge, and the linearization in the wake. And in sort of the particular like traveling waves context, you can use something called Palmer's theorem to compute this essential spectrum. And so hypothesis 1 is all about the dynamics in the leading edge. And so that tells us about the essential spectrum associated to the leading edge. And when we were talking about this marginal pointwise stability earlier, I used this exponential weight as sort of a nice thing to help me find the marginal pointwise stability. So here we get that the spectrum of L is marginally stable, the essential spectrum, if we use that same exponential weight. So we look at L in sort of a weighted norm, and then we get this in a function space marginal spectral stability. So then hypothesis 3, we're just assuming that this other curve of essential spectrum associated to the state in the wake is strictly stable in the left half plane. And I have this little asterisk here because I want to point out that this is the step where, for now, I'm excluding pattern forming fronts, because I'm assuming that this state in the wake has strictly stable spectrum. This spectral curve doesn't touch the imaginary axis anywhere. It's fully in the left half plane. And that's going to be violated for pattern forming fronts, which I'll come back to later. Okay, so that excludes any additional instabilities in the wake, but I still need to exclude localized unstable modes in the front interface. So to do that, I look at my linearized operator L, and I assume that it has no unstable eigenvalues. And so no eigenvalues with non-negative real part. And then farther, I assume that there's no bounded solution to this equation LU equals 0. So this is basically what you were asking about before. This is basically like I'm assuming that this coefficient's not 0, this A, so that I don't have a bounded solution to this equation. If you're familiar with, if you've ever heard of things like the Evans function and the gap lemma, what this condition is saying is that if you continue the Evans function into the essential spectrum with the gap lemma, there's no root of the Evans function at the origin, the analytically continued Evans function. So this is kind of saying that there's no eigenvalue embedded in the essential spectrum at the origin. The only marginal stability is essential spectrum, no embedded eigenvalue, resonance pole, anything like that. If you're not familiar with the Evans function or gap lemma, you can just ignore that comment. Okay, so those are our 4 assumptions that make this notion of marginal stability precise. So then under those 4 assumptions, we can prove our main result, which says that under those hypotheses, pooled fronts are selected. So that is, there are non-empty, open in a natural topology classes of steep initial data that propagate with the speed, the linear spreading speed, up to some higher order terms, and resemble this selected front for all sufficiently large times. So your solution is propagating with the linear spreading speed, and it looks like this critical front. Now you have this sort of like non-vanishing correction to the position, which is at lower order than the one from the speed, but it has this log t correction. And this log t was established for the Fisher KPP equation by Bramson in the 70s and 80s, but it's sort of predicted to be sort of a universal feature of pooled fronts by Ebert and Van Saarloos in 2000. So in addition to confirming propagation with the linear spreading speed, we also confirm the universality of this logarithmic delay. Okay, so that was the precise formulation of our main result. Now I just want to talk a little bit about some of the key technical aspects. So I motivated this whole thing to you, like why marginal stability, by saying that, okay, if we pick this linear spreading speed, then our tail dynamics in the leading edge can be constant in time, and that can let us glue with this front in the wake. But the dynamics in the leading edge, they're governed by an equation that looks like the heat equation. It has some higher order derivatives, but let's ignore those. Let's say it's like the heat equation. And solutions to the heat equation aren't actually quite constant in time, right? They're not exponentially growing or decaying in time, but they have some algebraic decay, right? If you solve the heat equation with some localized initial condition, you get some t to the minus 1/2 decay, something like that. So here, it actually turns out we do a little bit better than that, because this front back here is the state in the wake is exponentially stable. So it's like we're solving the heat equation, but with an absorbing boundary condition at the origin, and then we're solving it on the half line, and that improves the normal t to the minus 1/2 decay from the heat equation to this t to the minus 3/2 decay that I've written here. But that's still not constant in time, right? So I lied to you a little bit before. And that's why you need the logarithmic delay. So the logarithmic delay is chosen to sort of combine the interaction of this t to the minus 3/2 and this exponential decay here to make the dynamics in the leading edge constant in time. And so if I go to this moving frame with this logarithmic delay, then I get something like this, where I've got rid of this t to the minus 3/2 decay, and now I can hope to match with something that looks like the front in the wake. Okay, so now I want to talk about sort of a subtle point. So when I started, I was talking about I want to understand spreading from steep initial conditions or compactly supported initial conditions, this kind of thing. So I just want to point out that that's different from earlier results on stability of traveling waves against very localized perturbations that don't change the tail behavior of the traveling wave. So if I have one of these front solutions, I can look at a perturbation like this that is, some perturbation of my traveling wave, but I'm not changing the tail behavior. My traveling wave, my initial condition is still converging to 0 in the same way that my original front is. And those perturbations, they'll decay back to 0 if they're small enough, and they won't change your front's position, and you won't see this logarithmic delay. Those will just decay all the way back to 0. This logarithmic delay comes from the front's tail having to rebuild itself, which only happens if you actually cut off the front tail. So these very localized perturbations, they decay back to 0, and they decay with this rate t to the -3/2. And these were sort of stability of these kinds of fronts, and this kind of framework was studied by Kirk-Gostner in 92 for the Fisher-KPP equation, and a more general setting by Rogel and Kirk-Gostner in 98. And the sharp t to the -3/2 decay rate was obtained by Gallet, and then reobtained using different methods by Fay and Holzer, and also myself and Arndt, and for more general equations by myself and Arndt. So those results don't get what I want, though. They don't get spreading from steep initial data. They just get some kind of sort of very local stability result. So when you're spreading from steep initial data, you really have to look at, instead of just the front, you have to look at this refined approximate solution that captures these diffusive tail dynamics. And then you glue that to the front and you get an approximate solution to your equation. And you want to show that this approximate solution is stable in some sense. And because you have these tail dynamics baked in, now you can understand steep initial data. That's sort of the key idea there. Now, what makes this hard is that we chose these we chose the speed and chose this logarithmic delay exactly to make these tail dynamics not decaying in time anymore, right? So that we could match with the front. And so that means that if we linearize our equation here, try to study with this logarithmic delay in here, we're not going to have decay anymore in our equation because we chose the logarithmic delay exactly to get rid of the decay in our equation. And so you kind of have to work a little and sort of leverage the fact that if this logarithmic delay wasn't there, we would have good linear decay estimates. And you sort of play around with your equation, sort of bootstrap a couple times, do some stuff like this. And you can eventually close a stability argument for this approximate solution, where again, I want to emphasize that the key ingredients are, first, that you can construct this approximate solution with this diffusive tail, and then we need the sharp local stability theory for this front. That's what we sort of use, that I'm saying up here, to close this argument, that if this logarithmic delay weren't here, we have these sharp stability estimates, and we sort of use those. I think I will skip this pretty much. This is just saying about how we prove these linear stability estimates. And so there's this sort of very well recognized approach of Zumbrun and Howard, saying you can do this using what are called pointwise semigroup estimates. So I'll just basically skip past this. Arndt and I do this a slightly different way, where we use sort of a more direct functional analytic approach, but that still lets us handle these sort of subtle diffusive stability problems. We have this critical essential spectrum. Okay, so now I want to talk about how you can actually verify these assumptions. So the main issues, so the linear spreading speed, that's algebra. You can do that, or do that on a computer if you really need to. So then the main issues are to construct these fronts, and like you asked about, show that they have those generic asymptotics that you want, these Jordan block asymptotics, and then also to show that they're spectrally stable. So the way we do that is we look at our traveling wave equation and we make an ansatz that captures exactly the kind of decay we want to see. So this is some cutoff function chi plus here. And we assume that our solution is decaying to 0 in exactly this way that we want it to. And then W is some exponentially localized correction. And then here we're just making sure that we converge to the right state in the wake. This is some chi minus. So the two things to solve for here are this exponentially localized correction and this far field parameter A, this coefficient in here. And using Fredholm properties on exponentially weighted spaces, you can solve this equation if nearby a known solution with the implicit function theorem to construct fronts that way with these generic asymptotics, or you can stick this ansatz into your computer and compute this stuff numerically. And doing that actually gives you sort of good numerical algorithms for continuing solutions and tracking when this when this parameter A becomes 0. And as I sort of alluded to before, the bifurcation to push fronts happens exactly when this parameter A goes to 0. So you get a sort of very good numerical algorithm for tracking bifurcations from push to pulled fronts by implementing this. Okay, so I'll talk a little bit, I'll finish up soon, but just talk a little bit about applications. So first thing, these hypotheses are robust. You perturb the equation a little bit, this all sticks around. Basically using the ideas I had on the last slide for continuing front solutions and continuing spectral stability. So, and you can even in some settings handle singular perturbations to higher order equations. So in this paper with Louis Garino, we looked at a perturbation to the Fisher KPP equation where you add a small fourth derivative term, and you can prove that everything persists there. Now, this is an interesting thing. So you consider some reaction diffusion system, and what you assume is that the nonlinearity, the reaction kinetics, undergo a transcritical bifurcation as this parameter mu is varied. So you have this sort of normal form for the transcritical bifurcation here, and then the other components are stable. So you have an equilibrium that's losing its stability in a transcritical bifurcation. And then you can prove that near this bifurcation, you have spreading with this selected linear spreading speed. So basically, you're sort of capturing some universal features of spreading near bifurcations in reaction diffusion systems. And you can also do this near saddle node or supercritical pitchfork bifurcations. And this sort of is inspired by some ideas from this paper of Rogel and Kirk-Gassner, where they looked at similar things, but sort of proving different things and with, different perspective. Okay, now I'll just quickly mention some applications here. So this is a Keller-Siegel model for chemotaxis. We're interested in this setting where the chemotactic parameter is positive. So the population U is repelled by the emitted chemical rather than attracted. So we call it chemorepulsion. And then in this singular limit where chi is large relative to the diffusion coefficient in the second equation, we can sort of, in this limit, fully characterize the selected front solution. So we can find sort of where there's this bifurcation from push to pulled fronts, so that on one side we have push fronts with a speed that we can compute expansions for. On the other side, we have pulled fronts with the linear spreading speed, and we can get expansions for this transition point in terms of this singular parameter delta. I'll skip this application for now. So this is just an interesting model for some tumor dynamics where you have a competition for cancer stem cells and tumor cells, but you have some terms which sort of break the full competitive structure, so you don't have a comparison principle anymore. And depending on the parameters here, in some settings, you get a staged invasion process where one type of cell spreads first and then the other sort of invades in the wake, or you get sort of a more classical invasion process where they both spread together. And using these ideas, you can prove in some limits in this equation that this is what happens. Okay, so I just want to finish up really quickly by talking about some progress towards pattern forming invasion fronts, because that's kind of what I started with, showing you these videos of these pattern forming systems. So let's look at this Fitsu Nagumo system. It doesn't really matter exactly what it looks like, but this is this PDE system where the ODE dynamics, if I ignore the diffusion, have just one unstable equilibrium, and otherwise are sort of governed by periodic orbits in time. So if I look at a perturbation to this unstable equilibrium where I have small random noise everywhere, so I'm perturbing everywhere at some small amplitude, then this is what happens. So I see these temporal oscillations, but spatially there's not a lot of coherence here, right? I have these oscillations, but they're sort of happening at different phases because of this randomness in my initial condition. So if I just look at these random initial conditions, there's not a lot of spatial coherence here. But if I instead look at just a perturbation, a localized perturbation here near this left boundary, then this is what happens. This perturbation grows into a spreading invasion front that now sort of synchronizes these oscillations in this way, so that instead of having no spatial coherence, I'm forming this periodic wave train as I'm spreading. So here there's sort of a lot of spatial structure coming from this invasion process where there was none before in the absence of the invasion process. And then the key technical difficulty here is that these periodic patterns also only have marginally stable essential spectrum. So you have to deal with sort of two different kinds of marginally stable spectrum, one coming from this spreading in the leading edge, and then one coming from the periodic pattern in the wake. But we are able to prove nonlinear stability of these fronts under localized perturbations, but getting sharp decay rates. So this is kind of, like I said, a key ingredient to closing this front selection argument is a sharp stability theory for localized perturbations. And we're able to get this here for these pattern forming fronts. Okay, so I want to stop there. I'll just say that, again, the main message was that you can sort of, in a broad classes of models, predict these invasion speeds via these marginal stability conditions. And there's a lot of settings where you can verify these conditions either analytically in some limits or numerically. Okay, thank you.
Thank you, Monty. Wow, very deep talk, and but your talk is very comprehensive, really. Good.
Thank you.
Amazing. So, any question, comments, remark from the audience? Just unmute your microphone and just ask. Maybe let me begin. Okay. So I have an impression that this is all about the stability analysis.
Yeah.
Right. And I mean, this is not a question. It's just a comment I want to confirm with you. Like, and this and your theory is basic. You want to determine the basing of the traveling wave, and there's a family of traveling wave, but only the marginal one has an open basing.
So what I would say, all of them have some open basin, all of the stable ones, but the ones with the faster invasion speeds, their basin only includes these kind of perturbations that don't alter the tail dynamics. So what our theorem says is that this critical one, the marginally stable one, its basin of attraction includes some steep initial data, some data that vanishes, that cuts off the front tail. And that's not true for any of the other fronts.
I see. And the steep initial condition is so special because what?
So because, like, in sort of a lot of these experimental settings, like you think that you want to understand some spreading from compactly supported initial conditions. Like if you think about like an ecological model or something like Lac Volterra or something, you introduce an invasive species or something at one location and you want to understand the spreading. So steep is sort of, instead of looking at compactly supported, let's try to focus on just one front interface. So that's where steep plays a role.
So the critical one has an open basing with respect to the steep initial condition.
Yeah, that includes steep initial conditions. Yeah.
Interesting. Okay. Maybe let me continue my question. And because I told you, me and Beyond the Right, we are interested in control stabilization, right?
Yeah.
So, for example, I know the critical one has a, it's selected, and all the others are not selected. But suppose I want to introduce a control such that I want to select another one. What do you recommend? I need to which hypothesis should I focus, and then decide my control to change it to to change the selection.
Yeah. So these pooled fronts, they're really sensitive to what does the tail of my solution look like? How is my solution decaying to zero and stuff like that? So, and that's sort of one way to, that's also one difference between, these critical fronts and the faster fronts. as you increase the speed, you also change the convergence rate, how
Yes.
fast this thing's converging to zero. And so one way that you could probably see other fronts is stick in some term in your equation that decays, like e to the minus a to x, where a to x is one of these decay rates instead of this one. If you sort of stick that in as like a forcing term, then you can probably change the spatial decay rate of your solution in the leading edge, which will probably lead to it changing the speed. And there are sort of ideas like that. Or that idea is kind of relevant in some papers of like Matt Holzer, Greg Fay, and Arne Schiel, where they look at how sort of coupling to a different equation can change this tail behavior and sort of have that effect there, where by changing the tail behavior of the solution, you can change its speed.
I see. Yeah. Maybe if possible, I can present my work in your seminar, and you can understand better about this stabilization technique.
Yeah, that would be really interesting. Yeah.
Because I haven't provided you enough details, so maybe but interesting.
Yeah.
Yes. So questions, comments?
Hello.
Yeah. Hello.
Hey, hello. Thank you for your very nice talk. My question is very elementary. So in your page 9, you introduced the concept about essential spectrum. In page 9, yes, this picture. So I'm wondering, in the left case, the blue curve is essential spectrum, right?
Yeah.
So what equation can obtain such kind of essential spectrum?
Like a curve that looks like that. Yeah. So the curve that I'm plotting there would, for example, be the essential spectrum in exactly this equation. So yeah, that curve kind of looks funny if you're not used to seeing it. It kind of has this branch point at the origin and then came off this branch point. And that's what you'll see if you have an equation that the lowest order term is like the heat equation, and then you have some higher derivatives. Then you get something that looks like that. And so the essential spectrum that I was showing you is really the essential spectrum after you use this exponential weight. That makes the spectrum look like this, and that captures the pointwise growth or decay. So was something I was kind of sweeping under the rug at that point.
Oh, I see. So so in the left picture, it corresponds to the scalar equation with p partial x like this form.
Yeah, like yeah. And so this curve, what this curve is this is like lambda of ik equals, or lambda of k equals minus k squared plus order of k cubed terms. Then you get a curve that looks like this.
Oh, thank you. So what it means? There's a symbol D, a capital D, EFF. What's the meaning?
Oh, yeah. So. Yeah. So this, what I mean is it's an effective diffusion coefficient. So it's like, once I do all of this, I choose my C star and eta and use this exponential weight, I make my equation look like this. And whatever coefficient of the second derivative here is what I call my effective diffusion coefficient. And so I'll point out that like this doesn't rely on the original equation being like parabolic or just second order. This happens in higher order equations. You can get this kind of stuff in non-parabolic equations. It really comes from this like marginal pointwise stability mechanism. So somehow your equation, you end up with this diffusion coefficient here. So I call this the effective diffusion coefficient in the leading edge.
I see. Thank you.
Yeah.
So Monty, could you please go to page 36?
Yes. Yeah, here we are.
And if I do not misunderstand you, I think this construction of the approximated solution with a correction, this logarithmic delay is important for your analysis.
Yes.
But now if I give you a system, I give you an equation, a priori you don't know the speed. So then later you say you have a linear some, like semi-group analysis to find a
Yeah.
speed. But this is a daily analysis I expect. But do you have a heuristic way, like rescaling, some kind of easy way to guess the speed, to guess
Yeah.
the
So the first thing I would do if I was like presented with an equation and trying to guess the speed is I would compute I would compute the linear spreading speed according to double roots of this dispersion relation.
I see. Of course.
Yeah. And
yeah.
yeah. But I mean, it's still a good question because that will give me the right speed if there's a front associated to that speed that has these right asymptotics and that front is spectrally stable. So that can go wrong. That front can have an unstable eigenvalue. Right, that happens sometimes. Like for example, in like a scalar like Nagumo equation, sometimes the fronts are pushed. So then what I would do is I would change a parameter until somewhere I have a pulled front. And then I would numerically continue that pulled front until I see it change to a pushed front.
I see. But whenever you guess the correct one, you don't need to prove that, right? You can just use it to prove your marginal stability conjecture.
Yeah.
Yeah, I see. Cool. Now I have a nice question. But now why is this conjecture still conjecture? You have already solved it.
Yeah, I mean, this kind of happens, right? I guess like people still call the Poincare conjecture, right? They don't call it like the Perelman theorem. Sometimes names kind of stick like that.
You don't want to change your name?
I'm okay. I think it's a nice name, marginal stability conjecture.
Okay, cool. So basically, if I understand correctly, so the next step is to study oscillatory stuff, periodic pattern,
Yes.
like
Yeah.
also pattern forming condition and also bifurcation, something like that.
Yes. Yeah.
Okay, I see. Cool. So other questions, comments, remarks? Yes. Yeah, really amazing, really.
Thank you.
Okay. So if this is not the case, let's take the speaker, Monty, again. Thank you.